rewrite this as minus limit n goes to 1 trace rho to the power n over n minus 1. To see that, so whatever is in the brackets, I can write this as trace rho a e to the power n minus 1 log rho a divided by n minus 1. Expand it, so this is trace, so this is in the limit n going to 1, so I can do a Taylor expansion of this, so this becomes trace of rho a plus rho a n minus 1 log rho a plus n minus 1 squared, so on, divided by n minus 1. So in the limit n going to 1, this part is going to survive, but trace of rho a is trace of so this part is going to survive, and I'll be left with that. Okay.
This is in mind zeta function calculation of determinant. Is it related to some zeta function, some operator?
So in the formal way of that, we do we implement the replica trick in quantum field theory. It is related to the zeta function calculation, but then there the reason why you need to regularize is because there are infinite number of modes, whereas here, so here this n corresponds to the power of the density matrix. So it's not this n is not that not related to that, but these intermediate quantities that you're calculating, so this SNs which are defined as trace of rho to the power n a over n minus 1, these have a name, these are called Renier entropies. These are called Renier entropies. Yeah. So there's another useful way of rewriting this entanglement entropy, and that is in the following way. If I define Zn to be trace rho to the power n, or rho a to the power n, I'm dropping the subscript, then entanglement entropy can be written as the derivative of log of Zn minus n log of 1. And all this is evaluated at n equal to 1. So this just follows from this definition. Right. Okay. So if you were clever enough and if we had the resources, we'll be able to do this calculation in quantum field theory. But of course, there are problems if you wanted to do it in a quantum field theory. Then I'll try and explain what these problems are. The idea in holography is to assign each of these quantities in this expression with geometry. So there's a geometrical way of understanding each quantity. And in tomorrow's lecture, if I get time, or if you want to ask me in private, this was what Decomposition and Aninda Sinha taught us this year.
Should I have a clear interpretation of those?
Yes. Yes. Well, in the limit n goes to 1. Yes. Cleaner for each value of n. There's a cleaner way of understanding the geometries. It corresponds to this map from the circles to the hyperboloid, and then associating with the thermal entropy, which maybe I'll explain to you. Okay. So another useful basic piece of information is what is called a Schmidt decomposition. So if you have a pure state psi, and say psi can be written as in the following way, that psi is summation C and M A sub n B sub n, where A belongs to the Hilbert space HA and B belongs to this Hilbert space HB, and psi can be written like this. And if psi is the Schmidt decomposition tells us that this can be rewritten as summation lambda n A n red product E n. So in a sense, you've diagonalized your C and M, and you're left with just lambda n's. So this plays a very important role in this bipartite entanglement. So bipartite means that you have two regions or two subsystems, and I should point out that this does not extend, this Schmidt decomposition does not extend to tripartite systems. Does not work. And the intuition is very clear that if you have a tripartite system and suppose you measure one of the systems, then the other two still could be entangled. Okay? So that's the intuition that why this decomposition does not work for tripartite systems. And only for very special kind of states does this work, that if you do measurement on only one system, you get to know the information about the rest. And those, so one very famous example of that kind of a system is what is called a GHZ state, Greenberger, Horn, Zeilinger. So an example is this. After some normalization, so you can see that if you make a measurement on the first system and you find that the spin is pointing up, then automatically you know the information about the other two because this is the state. So there's no ambiguity. This guy is does not contribute there. Okay. So with this basic, let me tell you a very key theorem in quantum information about relative entropy. And I'll prove that theorem. I guess so hopefully this will be useful for the students. So let me tell you what relative entropy is. So relative entropy needs, in order to define relative entropy, I need two states, call them rho and sigma. So these are the density matrices corresponding to the two states. Then the relative entropy is defined in the following way. The notation is this: rho big dash sigma is trace rho log rho minus trace rho log sigma. This is the definition of relative entropy. And in tomorrow's lecture, I will give you examples of how to check the following. So there is a famous inequality which I'm going to show you how to derive in a bit. It's called the Klein inequality, which says that this is greater than or equal to 0. So in some sense, it gives us a measure, because it's positive, it gives us a measure of how far the state sigma is from the state rho. It's not really a metric measure because it's not symmetric under the interchange of rho and sigma, but then it does give us a measure of some kind.
Are you sure there is no overall minus sign?
I'm sorry?
There is no overall minus sign?
No. It is with this sign. No overall minus sign. I'll prove it to you just now. Okay, so there are two states. This is state 1, this is state 2. Okay, so let me prove this statement. The proof is very simple. So you consider the orthonormal decomposition of rho and sigma. Consider the orthonormal decomposition of rho and sigma. So I'm writing rho as summation over I pi like this, and I'm writing sigma as summation over j qj like this. pi log pi. I'm tracing, so trace means I'm writing down the expression for the operators and I'm putting i's on both sides and summing over all the i's. That's how I get pi log pi. The second term is minus summation over I rho log sigma I. So rho acting on I is going to bring out pi. This is minus summation I pi I log sigma and I. Now at this stage I will put in a complete basis given by this j. So I will need to sum over j. So I do this. When log sigma acts on j, this is going to become log of qj. And this is just a number, so I pull it out. So that's what it is. And this quantity I'll define as pij. So this becomes some minus summation pij little pi log little qj. And you can readily verify that this pij satisfies some nice properties, that if you sum over the i's or the j's, I this is equal to 1, or if you sum over j, this is also equal to 1. When a matrix satisfies this condition, it is called it's got a nomenclature, some terminology, it's what is called doubly stochastic. Of course, this is just terminology. This does not take out. Okay. So now there's a very important property that this log function that this log satisfies. Log is a concave function. Log is a concave function. Concave function is 1. So in particular, let me just write down the relations. Log of px plus 1 minus py is bigger than or equal to p log x plus 1 minus p log y. And here p lies between 0 and 1. So using that, we can rewrite this as minus, so that quantity that I've written there is simply summation pij log qj, and this is bigger than or equal to minus log summation pij qj. So I've just pulled in the pij factor here, and this inequality follows because of this. This quantity, let's call it ri. So then what I get is S rho sigma is greater than or equal to summation over I pi log pi divided by ri. And let's write this as the right hand side of this inequality, let's write this as minus summation over I pi log ri by pi. Okay. So it's greater than or equal to something. There's one more step that I need to show that this quantity is greater than or equal to 0, and that will complete the proof that this is greater than or equal to 0. So the next step of the proof is straightforward. In fact, so what you need to use is log of x. So all the logs that I've written here are with base 2. So that's why log times the natural logarithm 2 is the natural logarithm of x, and this natural logarithm of x satisfies the following inequality: it is less than x minus 1. So that means that minus log of x is bigger than or equal to 1 minus x over ln 2. Using that, this quantity becomes bigger than or equal to over I, pi divided by log 2, 1 minus ri over pi. Then pull this pi through, the summation over pi is 1, the summation over ri is 1, so this is greater than 0. Okay, so that completes it.
What did you say you used it now?
Right?
Do you think you said about the composition of the thing you raised on the right hand side of the blackboard?
Yes.
This is only true for systems that two Hilbert spaces are the same, right? You're breaking up into the product of two equal zero of the same dimension.
No. So here, they could be they could be
No.
different. Yeah.
No, I agree this is true, but you wrote there that you can always write any
The Schmidt decomposition.
Yeah, that's true. That's only for space for breaking where the two Hilbert spaces are the same dimension.
Right. Yeah.
You haven't used that.
No. I'm not used the Schmidt decomposition anywhere here.
Ah, okay.
Yeah.
Okay.
Hang on, question.
Yes.
I thought the Schmidt decomposition applied even when the Hilbert spaces were not the same size, and the number of terms in the sum is equal to, is at most the dimension of the smaller Hilbert space.
Right. Yeah, because you can easily extend it by putting in additional operators. If the dimensionality are not the same, so what he's saying is that.
That's true, but you have to decide on a basis, right? You don't know what basis it is.
No,
But there is a basis.
There is a base, but you don't know where it is.
Well, given the state, you can figure out the basis.
You can say, okay, that's true.
So all that you're saying is that I can enlarge this matrix, which may not be a square size, to fill in zeros and make it into a square matrix.
But the statement is different, right, from a symmetric system where you can always write it like that and then figure out what the basis is. Right? If the two Hilbert spaces are the same dimension, you can just write it like that and then figure out.
Sure, but the Hilbert spaces that you start with don't have to be the same.
I understand.
They don't have to be the same dimensions, yes. Okay. So let me write down some properties of this one Neumann entropy. And some of these properties can be derived using this notion of relative entropy. So the first properties of one Neumann entropy. So this is non-negative. This is obvious. And this is 0 only if and only if the state is pure. Second property is that in a d-dimensional, so this is for finite dimensional Hilbert spaces. In a d-dimensional Hilbert space, this entropy is less than or equal to log d. This is very easy to prove using this relative entropy. So the relative entropy is supposed to be bigger than or equal to 0. So you take sigma to be I by d. So this is identity matrix. So sigma is a matrix which has got entries along the diagonal, that's 1 over d. So if you do that, then this becomes, left hand side becomes trace rho log rho minus trace rho log sigma. This is trace rho log rho, and this is plus trace of rho times log of d. So each entry here is 1 over d, so that's why we get this plus sign, and this trace of rho is 1, so we can get rid of that. And then, so this is bigger than or equal to 0, but this was the definition of S of rho with the minus sign. So this means that this implies that S of rho is less than or equal to log d. Sorry, prove it. The other thing that you can prove, and this is actually quite important, is that if A and B, so AB is a composite of, which is a, so by system AB I mean it's a composite of system A and composite of system B, composite of A and B. And if this is pure, if A and B is pure, then SA is equal to SB. And this just follows from the Schmidt decomposition. So you write psi as summation lambda I IA, IB, and then what you find is rho A is summation over lambda I square IA, IB, sorry, IA, and rho B is also lambda I square IB, IB, and so from here you see the eigenvalues are the same, so this is true. And this formed the basis of an observation that Schmidt made in 1993, that in a quantum field theory, suppose you divide up the region where your quantum field theory lives into two pieces, A and B, then since SA is equal to SB, what is common between these two systems? So the only thing that is common between these two systems is this boundary of the region. So that forms the basis of this area law, that because the boundary has the dimensions of the area, so the entanglement entropy should also be proportional to the area. So that is a rough way of understanding where this area dependence for the entanglement entropy comes about. Okay. Since I'm doing very badly with time, let me just go ahead. There's another property, very important property. So this was 1, 2, this was 3. Important property that this one-norm entropy satisfies is what is called subadditivity. So I told you to be on the lookout for this terminology. In fact, I told you to be on the lookout for strong subadditivity. So let me tell you what subadditivity is, and then I'll tell you what strong subadditivity is. Subadditivity means that if I want to compute the one-norm entropy of a composite system AB, then this is less than or equal to SA plus SB. Proof is again quite simple. All that you do is you substitute in this relative entropy, this inequality, you substitute rho to be equal to rho AB, and sigma to be the direct product of rho A times rho B. Then the left hand side is going to tell you that, so what you have is, so trace rho log rho is greater than or equal to trace rho log sigma. That follows from the positivity of the relative entropy. This is minus of SAB, but on the right hand side what you get is trace of rho AB log rho A plus log rho B. It splits up into a sum because it's a direct product. And then when you are talking about each quantity, so although this is rho AB, because this only acts on A, this simply becomes trace rho A log rho A plus trace rho B log rho B. But this is nothing but minus S of A. This is nothing but minus S of B. So that's how it follows. So this is subadditivity. Strong subadditivity. So this is the strong subadditivity is a very important non-intuitive concept that this entropy satisfies, and it's very hard to prove in quantum mechanics. It's very lengthy. The proof is very lengthy. If you're interested in finding more about the proof, there is a book on quantum information and quantum computing by Nielsen and Chuang. You'll find the proof there. So the statement of strong subadditivity is the following, that if I have three systems A, B, C, then SBC plus SEB is bigger than or equal to SABC plus SB. This is the statement of strong subadditivity, and I will show you how the proof works in holography towards the end of this lecture. that was property number 5. There's also a property number 6, but this one, the status of this is a little less clear in quantum field theory, which is called monogamy of entanglement. Stefan, are you going to talk about this?
Yes, at least a little bit.
But then, yeah, the version that goes into firewalls probably does not use this statement, right? I'll write on the statement, monogamy of entanglement. The easiest way of defining monogamy of entanglement, and in fact, the easiest way of stating this inequality is also through something called mutual information. Again, this is terminology, but this is just to make life a little simpler and to remember these inequalities. So, the mutual information, by the notation for mutual information is A colon B. This is simply S of A plus S of B minus S of AB. And in terms of this notation, I A colon B, which is just this, the monogamy of entanglement can be written as A colon BC is bigger than or equal to I A colon B plus I A colon C. This monogamy comes, it's just follows from the notion that you don't want to have more than one wife at a time. That's why that is the that's why it's called monogamy. I mean, that's where it comes from. So if you are maximally entangled with one person, then you cannot simultaneously be maximally entangled with another person. That's what is. I wonder how. Anyhow, so. Great. So before I move on to the basics of EDA safety, I need to tell you how entanglement entropy is computed in field theory.
But this inequality is not the same as Bell inequality. The structure is very similar.
Yeah, but Bell inequality has to do with simultaneous measurements. For three events. I'm not sure how to correlate it with an entropy, but maybe there is something. I don't know. So what you're saying is,
Structure is.
Yeah, structure is very similar. Yes, I agree. Okay, so I need to tell you how.
This is not using quantum mechanics.
This is just using quantum mechanics. What?
This is not using quantum mechanics.
This monogamy of entanglement.
It's not a quantum mechanical fact. I mean, this is true in general, right? Even if you have, and this statement of
This
density
particular,
matrices.
yes.
It's just a statement about density matrices. It does not rely on quantum mechanics.
Right. Sure.
So the Bell inequalities do depend on quantum mechanics. This is not true. Classical
Yeah,
system.
but the statement of the inequality might
Okay,
depend
actually,
on quantum mechanics, but whether it is true or not.
Sorry.
Bell inequality actually contradicts quantum mechanics. It assumes hidden information.
Well, it's a statement of what quantum mechanics needs to satisfy, right?
Yes, I mean if it's the other way around, so it has to be greater than 2 root 2 or something like that.
That's right. So the statement of quantum mechanics has to satisfy, right?
If
Well-
you have hidden variables. So it's
Yeah. So if you could measure everything, right? So in a sense, well, this is true for any system. A classical system that has some density measures has to satisfy this as well.
Yeah, except that as I said, this monogamy of entanglement, the status in quantum field theory is not clear. Because there are examples in quantum field theory where this definitely or whatever we know. But monogamy of entanglement we don't. Anyhow, so let me tell you how entanglement entropy is calculated in free quantum field theory. So this is just background still. I won't be using any of this, but then this is just to set up what it means to apply the replica trick and where the difficulties arise. That will become clear through this example. So entanglement entropy in free quantum field